Good afternoon, students. In the last class, we discussed about the ellingham diagram and the application of the ellingham diagram. How the iron is extracted by using carbon, at what temperature iron is extracted. Right. Okay. I think you may not see that clearly. So once I'll explain the application of ellingham diagram in the extraction of iron. Okay, students. In that, I taken a diagram like this. This is delta G of formation of oxides, and this is T, that is temperature. Here 400, 800, 1200, etc. Okay. So assume this is one point. At this point, this is carbon curve, C plus O2, CO2, that is carbon dioxide curve, and this one is C plus O2, that is CO, carbon monoxide curve. And this one is Fe plus of O2 gives rise to Fe4. Okay, so this is the curve. So listen students, as I explained yesterday, so this is 0 degrees Celsius, correct? So it is nearly 400, this is assume 500, so this is minus 500, this is minus 400, this is minus 300. Okay, I said the same thing. So this is for just an assumption. Again, I am telling you students. So here, iron curve has minus 400, minus 500 delta G value here. Okay, this carbon has minus 300 delta G value here. So in that case, so what we can say, at the lower temperature, which is below 400 degrees Celsius, or at this temperature, assume this is 600. Okay, so below 600 degrees Celsius, this iron has the capacity to reduce this carbon as well as carbon. Okay, both the carbons, carbon dioxide as well as carbon monoxide. So this shows what? The curve at 0 degrees Celsius, iron curve is below the above the carbon curve. So this shows what? Iron reduces carbon at a lower temperature. So this, the red dot what I wrote here, this is the equilibrium point, and above this temperature. So above the 600 degrees Celsius, what happens? This carbon curve is here, this carbon curve is here, this iron curve is here. Sorry, okay, here. This is just above the carbon monoxide and the carbon dioxide. So here what happens? At this time, this carbon has the capacity to reduce this iron. Okay, so this is the selection of suitable metals to reduce the respective metal. So next one is applications of ellingham diagram. Okay, so in that applications of ellingham diagram, we extract three metals based on the thermodynamic principle. So first one is extraction of iron from its oxide ore, that is hematite. The composition of hematite is Fe2O3. Okay, next, second one is extraction of copper from its sulfide ore. Okay, from its sulfide ore, that is copper blacks, Cu2S. Okay, next one is extraction of zinc from oxide ore, that is zincite, that is certain. So listen, using thermodynamic principles we explain these three extraction methods: extraction of iron, extraction of copper and extraction of zinc. So we will discuss one by one. So the first one is extraction of iron from the ore, that is hematite ore. It is the oxide ore of what? Iron. So to the students, you need to take a diagram that is called as blast furnace. Okay, I will write the diagram. Okay, so this is a typical diagram of blast furnace. This is a typical diagram of what? Blast furnace. So here is a body of the furnace. It is completely made up of metal to sustain the temperature. It is an isolated material. Why isolated? I say isolated means heat cannot be, the exchange of heat cannot be takes place. Okay, so here we have open valves. Okay, so here we have container, here we have another container. So in this, different temperatures are there. Here 1070 Kelvin, okay, next 1270 Kelvin, next 1570 Kelvin, next 2100, 1000 Kelvin. Okay, so 170 Kelvin. So different zones are there. From here, air is fast. Now we come here. Here we have another valve. Here we have another valve. So here air will pass on both the sides. Hot air. Hot air. Okay. So here we have ore particle plus coke plus calcium carbonate. Ore plus coke plus calcium carbonate all are mixed as a powder ore here. You can write in that another color, you may clearly understood this. So this is ore particle, gan particle may be present in this ore plus coke plus carbon, sorry, calcium carbonate. This is the typical diagram of the what? Blast furnace. So students, here different temperatures are there. In the bottom of the furnace, high temperature is there. In the top of the furnace, low temperature is there. From here, the powder ore is fed into this blast furnace. Okay, so here what happens means, listen, the ore, the finely powdered ore is mixed with coke and calcium carbonate in a suitable ratio. Okay, so that is fed into the what? Blast furnace. So here what happens means, in the first, at this zone, so the temperature is less, at this zone temperature is high. So here what happens, the coke is there, Here the coke is already present. Okay, whatever the coke is fed into this blast furnace, what happens is that coke burns in presence of air. Okay, in air oxygen is present. Okay, so this coke is burned in presence of air, forms carbon dioxide. Okay, here it forms carbon dioxide. As I told you, students, so listen, first I write the typical reactions first. C plus O2 gives rise to CO2 means write delta G value is equal to minus 353 kilojoules per mole. So this is exothermic reaction means it releases heat. In the first year, the thermodynamic concept, you already learned about this. What is exothermic reaction and what is endothermic reaction. In that, the very simple reaction is this one to show which is exothermic means it releases energy. So listen, here I told you the coke reacts with oxygen, that is hot air is blown into the blast furnace. So here what happens, the carbon combines with O2, coke is nothing but carbon, forms CO2, the delta G value is 353 Kelvin. So at the same time, listen students, here hot air is there, obviously it is there. So at the same time it releases, okay, formation of CO2 releases an enormous amount of energy, results in high temperature at the lower of the blast furnace. Okay, lower region of the blast furnace. So this again what happens, this carbon dioxide move upwards. As it is a gas, it moves upwards. So here one valve is there. This valve is to escape CO2 gas. Okay, so here what happens, the CO2 gas formed here is moved upward this blast furnace. So then what happens, again the continuously ore is poured into this blast furnace. So then what happens, again coke is present here. That coke again combines with carbon dioxide which is just moved upward and it forms what? CO. Okay, this is somewhat an exothermic reaction means the temperature decreases. So that's why at this range the zone of combustion takes place. Okay, here what happens means the energy, sorry, not the energy, okay, heat energy decreases. So here the temperature is less. Okay, where the temperature is less, there the reduction occurs. Okay, this is combustion, this is reduction. So reduction means iron oxide is there, we are taking Fe2O3. This iron ore combines with carbon monoxide which is formed here. Here carbon monoxide is formed, how I already wrote here. So Fe2O3 reacts with this CO, forms Fe3O4. Here 3 times, here 2 times, plus CO2. This Fe3O4 again reacts with carbon monoxide to form FeO plus CO2. This FeO again reacts with carbon monoxide to give Fe plus CO2. So this is the reaction takes place in what? Reduction zone. Okay. So along with the students, we wrote the reaction for combustion, that is coke, and we did a reaction, reduction reaction for what? This iron. Okay. Another one is there, that is CaCO3. Okay. Here what happens? Another one zone is there, that is zone of slag formation. So what happens in the zone of slag formation means, so don't write this equation, okay, wait for me, I will write it clearly because it is very important for 3 marks in the annual examination. Okay, just wait. So slag formation means first this CaCO3, when it is heated, the temperature present inside the blast furnace, it decomposes the CaCO3 to CaO plus CO2. This CaO reacts with silica, that is gangue particle present in the ore. I told you in some already the concentration of ore takes place, at the same time the CaO some amount of some traces of what? that silica or sand, whatever may be, there may be a chance of presence of some amount in the ore. So then to remove that silica chemically we will use CaO. So then it is formed CiSiO3, that is calcium silicate. Okay. So students, this is GAN, this one is slag, and this one is flux. As I told you, flux is used in a chemical process to remove this GAN particles, or a chemical used to remove the GAN particles or unwanted impurities present in the ore particle during the time of extraction, that is called as what? Flux. Okay, this one is flux, this is GAN, and that one is slag. Slag means I told you it is a waste formed during the chemical process. Okay, so this is all about the reactions involved in this blast furnace. So in the blast furnace, three types of zones are there. One is combustion zone, reduction zone, and a slag formation. This combustion zone takes place at the range of 1773 Kelvin to 1873 Kelvin temperature. So that means 1500 degrees Celsius to 1600 degrees Celsius. It is in Kelvin, it is in Celsius. You know what is the relation between Celsius and Kelvin? So 0 degrees Celsius means 0 plus 273, that is 273 Kelvin. So Celsius is equal to, or Kelvin is equal to, say, degree Celsius plus 273. This is the relationship. Correct? Next, here this reduction zone takes place up to 673 Kelvin to 873 Kelvin. So sorry, 973 Kelvin. That means 400 to 700 degree Celsius temperature here in this zone. Okay. Next, slag formation, it takes place at 1073 Kelvin temperature to 1273 Kelvin temperature. So see, these are the different zones of the extraction of iron from its oxide. So that is hematite ore. Okay. So in that, what will you have to write? So what they will ask in the examination means, they simply ask, write the different zones of iron involved, different sources of blast furnace involved in the extraction of iron from its oxide ore. Okay, then ask the question like that. Okay, so listen students, I'll write clearly what you have to write in the examination. So you just note down these points. Whatever I wrote on the board, you just note down it. Okay, listen. So I told you this is the hematite ore, this is the oxide ore. So here in the complete extraction process in the metallurgy, three types are there. I told you first one is concentration of ore, second one is isolation of metal, third in that isolation of metal extraction is there. Okay. So how that isolation process takes place? Okay, I'll explain first. Here, first one is concentration of ore. So this is being an oxide ore. The concentration of ore, so this is consists of what? Only sand particles, such type of impurities they have. So the concentration process is hydraulic washing. Hydraulic washing. So students, this is not given in the NCERT textbook how this process takes place. So the concentration technique used to concentrate this hematite ore is hydraulic washing. Okay. So next, sorry, not hydraulic washing. Sorry. This is magnetic separation. Why it is magnetic separation means because iron is strongly attracted by what? Magnetic field. So due to that reason, both hydraulic washing also happen, and we can conduct hydraulic washing as well as magnetic separation. But the most preferable is magnetic separation because iron is strongly attracted by what? Magnetic field. Okay. In both are important. You may concentrate the ore by using hydraulic washing as well as magnetic separation, but this one is most preferable. Okay. So second one is conversion of oxides, correct? conversion to oxide. So here it is already an oxide ore. It is no need to convert it into oxide. We just have to remove any extra hydrated molecules are there. So that's why it is now don't need any oxygen molecule or presence of air to burn this or to convert it into oxide, being it is already an oxide ore. So calcination takes place. Okay, so after that, this ore is subjected to what this? So this ore is mixed with coal, this copper and calcium carbonate. Then the blast furnace process takes place. Okay, so in this process, three zones are there. So here you take blast furnace process. Okay, so in that first one is zone of combustion. In that zone of combustion, the temperature is 1773 to 1873 Kelvin. This is zone of combustion. So here what happens, students? The carbon or a coke reacts burns in presence of air to form carbon dioxide. Okay, so here coke means carbon, reacts with oxygen, gives or bonds in presence of oxygen, gives CO2. Okay, next the carbon dioxide so formed move upwards and again reacts with coke to form carbon monoxide. So this is carbon dioxide plus carbon gives rise to CO, that is 2CO. This is zone of combustion. So next one is zone of reduction. Next one is zone of reduction. So in this zone of reduction, what happens? The carbon monoxide formed reacts with iron oxide ore to reduce it to iron. So here the reaction is, the reactions take place here, students. First, this Fe2O3, That is what? Hematite reacts with carbon monoxide, forms Fe3O4 plus CO2. Fe3O4 plus CO2. Here it is 3 times. Here it is 2 times. Okay. Next, this Fe3O4 again combines with CO, forms what? 2FeO plus CO. Now 2FeO, it is 3FeO plus CO. Next, this FeO combines with CO gives Fe plus CO2. So this is the three reaction taking place under this reduction zone. This reduction zone temperature varies up to 673 to 973 Kelvin. 673 to 973 Kelvin. Okay, and the last one is that is zone of slag formation. In this zone of slag formation, the temperature ranges from 1073 to 1273 Kelvin. Okay, so what happens in this zone of slag formation is the CaCO3, the calcium carbonate, is heated means we form CaO plus CO3. Okay, this CaO reacts with SiO2, the silica present in the ore, form CaSiO3. Okay, students. So this is called as what? Flux. This one is called as blend. This is slag. Okay, this is the equation and this is the term process used in this blast furnace. Okay, if the has the right steps involved in the extraction of iron from the blast furnace, they never ask diagram, they directly ask the reactions. If you write these different three zones with correct temperature and the correct balanced equation, you will get complete marks, and this is very important for examination orientation for 3 marks. I told you the question number 19 is always from this chapter. So this is the one of the expected question for 3 marks in this chapter. Okay, so keep on practicing this, students. Okay, this is all about the blast furnace, that is extraction of iron from its oxide ore. Okay, next one is extraction of next extraction of copper from its sulfide ore. Extraction of copper from its sulfide ore, that is one copper gland CO2. Yes. Okay, students, in this, this is takes place in reverberatory furnace. First, I'll write the diagram of reverberatory furnace. Lining is there. Okay. Next, this is magnesite lining. This magnesite lining is to reduce the carbon. Okay. Next one. This one is taken. Not this one. Here, another one small chamber is there. Okay, the chamber also lined with those things. Here, hot air blowers are there. Here, hot air is supplied. Okay, next, from here to pillars are there and to rods are there to support the anchors. Okay, so from here two charged coppers are there. This is completely filled like this. This is the arrangement of what? Blast furnace. So here students, tight thread is there. This is subjected with this rods. Okay, tight thread is there. So here what happens? The thread is holding this. So this is what charge hookers. So this is tie thread or tie rod. Okay, this is tie rod. Next, this one is air and oil hose. We want air because this is a sulfide ore. It requires sufficient supply of air to undergo roasting to convert sulfide ore into oxide ore. Okay, so next one is this is magnesite lining. So this will do the carbon. This will provide the carbon and the production of carbon. And next one is this one is furnace where all the process takes place. Okay, and this is silica. Okay, so this is all about the extraction of copper from a sulfide ore. So students, here what happens means, listen, I told you we are considering what? Cu2SO. So here the principle involved is, last class we discussed about the Ellingham diagram. So that Ellingham diagram only we wrote the curves for the oxide ores, but we didn't do that for the sulfide ores because the extraction of metals from the oxide ore is quite easier than the extraction of metals from the sulfide. So we can do one thing, that sulfide ore is converted to what? Oxide ore. Once it is converted to oxide ore, in the last Ellingham diagram, the copper sulfate ore, copper oxide ore is at the topmost of the series. That in the Ellingham diagram, it is at the topmost curve. Okay, so that means even we choose any of the metal, it can have the ability to reduce the copper. At the same time, for better, we choose only carbon to reduce other metals because it easily forms CO2, that is a gas that easily escapes. Okay, so listen, here what happens? First, the concentration method takes place by froth flotation method. Froth flotation method. In the last class, I told the process of concentration of the ores. Specifically for sulfide ores, we prefer froth flotation. Okay, and at the same time, I said if the two or more sulfide ores are there, by adding the depressants, we can separate them easily. So the best method to concentrate the sulfide ore is froth flotation process. And the second one, conversion to oxide. Conversion to oxide. Okay, this conversion to oxide, what happens means, here we take roasting. Roasting means the heating of a concentrated ore, the strong heating of a concentrated ore in the presence of a sufficient supply of oxygen, that is air. That is called as what? Roasting. So then what happens, students, when these two done, so the process is, this is the principle actually, the process principle, what is principle means, so how this actually works in the blast furnace. So listen students, the given copper glance ore is powdered finely and it is concentrated with the froth flotation process, and again it is roasting takes place. While the roasting takes place, the Cu2S ore is converted to what? Cu2O. So that is all takes place in what is reverberatory furnace. Okay. So the process is this. I'll say in this process, ore, that is copper glance, is mixed with silica, and at the same time it consists iron as an impurity, that is slag. So this ore Cu2S consists of iron as an impurity. So in that process what happens means, so in the complete reverberatory process, the reaction I am write here, all the reactions which are all important in this. Okay. First what happens, this Cu2S is burned in presence of oxygen, gives Cu2O. Okay, so this is 2 times, this is 3 times, 2 plus 2SO. Okay, so students, while this happens, at the same time what happens means, this O and iron, this Cu2S and Fe combines with each other with the sulfide ore, forms Cu2S and Cu2Fe. This is called as copper mate, and this is very important for 1 mark. What is the composition of copper mate? So listen students, this copper mate is not a ore. Write the composition clearly because it is important. Cu2Fe. Okay, so this is very important. It is not ore of the copper, but it is formed when the copper and copper glands is heated in presence of SO2 and iron as the impurities in the reverberatory furnace. So this is important. Cu2 Fe(S). This is the composition of copper. So in that copper made Cu2S into 3SO4 forms what? That SO2. Again, Fes is there. It combines with oxygen, forms FeO plus SO2. That is 2 times, 3 times, 2 times. So this is the first reaction. So as I told you students, this will happen. Then we want what? Copper. Once the copper oxide is formed, it is easy to reduce with this carbon monoxide. So then what happens? Cu2S, it gives 2Cu plus CO2. Okay, here oxides will form, here reduction will be done, here oxides are formed, here reduction. So another one reaction is possible. This Cu2 again have the capacity to combine with Cu2S to form 6Cu plus SO2. So listen, this Cu2O again have the capacity to combine with Cu2S, then also it reduces to 6Cu plus SO2. So these two reactions gives copper. So I told you iron is present. Iron is considered as a impurity here. Okay, here silica is added. That means this FeO formed combines with SiO2 gives rise to FeSiO3, that is iron silicate. So yes students, in this case, this is impurity means GaN. This is impurity, that is GaN. This is GaN particle. This is flux. We use silica to remove this FeO, and this one is slag. Only these reactions are involved in the extraction of copper from its sulfide ore. The concentrated ore is flotation. The conversion of oxide is by roasting, and this is the process. So ore is mixed with silica and iron is present as an impurity. So once they are mixed with each other, then when it is subjected in a reverberatory furnace, it is converted to what? Copper made Cu2Fe(S). Once it is converted into that, then they are converted to what? Oxides. Okay, Cu2S, when this roasting happens means the Cu2S 3O2 gives rise to this copper oxide, this Fes gives this iron oxide. So this Cu2 is subjected with carbon monoxide, then it will give carbon dioxide as a metal. So here we can extract by using carbon monoxide also. At the same time, so this can also react with the Cu2S which is already present in the reverberatory furnace, then also it reduces to what? Metal. Okay, then this is iron is considered as an impurity here, that means a GaN particle, then it is a flux used to remove this FeO, and this is the slag compound, that is FeSiO3. So listen, all this GaN, flux, slag, what I am telling is very important for 1 mark. That's why I am mentioning here students. Okay, they may ask what is the slag formed during the extraction of copper. You may know the iron silicate, that is FeSiO3. Okay, so listen, in the last I said we will get a raw iron, here we will get a raw copper, here SO2 is liberated. Why I am telling? Just now I will explain. I told you refining method is there after this extraction, correct? So the iron we got from the blast furnace is called as what? Pig iron. Okay, so why it is called as pig iron? It consists of 4% of carbon and impurities like sulfur, phosphorus, silica, etc. Only small impurities it is. Next, it is subjected to some refining methods. Then it will changes to what? Cast iron. This cast iron is free from all the impurities, but it consists of 3% of carbon. Okay. So next, last one is wrought iron, which is free from carbon. Free from carbon. That means a pure commercial iron which we use to prepare the respective useful metals. Pig iron, cast iron, wrought iron. Pig iron means 4% carbon it consists of. Wrought iron means 3% carbon. A cast iron. Wrought iron means free from the carbon. So here, listen. Here, due to the production of SO2 gas, here copper forms a blister. Blister means a holes in the metal. Okay, that's why this is called as blister copper. So they may ask students why the copper extracted from river furnace is called as blister copper. Because of the evolution of the SO2, the metal surface, the copper metal surface forms a blister. That's why it is called as blister copper. So why the iron is extracted from the blast furnace is called as pig iron means because it consists of 4% of carbon and remaining impurities. Okay. Next, cast iron means the pig iron is subjected to refining when the impurities are removed and it consists of less amount of carbon compared to pig iron, that is 3%. That's why it is called as cast iron. The last one is wrought iron, which is free from carbon. So these are all important for one. What is pig iron, what is cast iron, what is wrought iron, and what is blister of copper. Okay, so this is all about the extraction of copper from its sulfide ore. So in the examination, you have to write only those. Okay, so this is also important for 3 marks students. So last one is extraction of zinc from its oxide. Okay, so extraction of zinc from its oxide ore. So here what happens? Zinc oxide ore is, that is zincite. Certain. Oh, here the concentration process is, I told you, hydraulic washing is an hydraulic washing, and the conversion to oxide, it is already oxide ore means it is calcination. Okay, the only one thing is there students, this LMO directly reacts with carbon monoxide at 673 Kelvin gives Zn plus CO2. There is only one reaction. It is also done in a furnace, electrical furnace. So directly ZNO is mixed with carbon monoxide at 673 Kelvin. If it is heated means directly gives zinc and carbon dioxide. So this is only one reaction. They may ask it for 2 marks, but in application of an Ellingham diagram, the most important thing is extraction of iron from blast furnace and extraction of copper using reverbatory furnace. These two are the thermodynamic applications in the extraction of metals in metallurgy. Okay, thank you students. So you note down all these things like this. So after that, I'll send the notes. Thank you.